So hello everyone, this series will be on thermodynamics, and in this we are going to study conduction, convection, radiation. In conduction we'll study lumped capacitance model, we'll study about Biot number, we'll study about fins, and we'll go and solve few questions in that. After that we'll go in RAC, refrigeration and air conditioning. After that, we'll go in engines. There we'll solve IC engine, EC engines. We'll see the theory part. We'll solve some questions. So let us begin. In this video, we'll cover one-dimensional heat flow and three-dimensional heat flow, and or we can say that conductive heat flow equation in three dimension. That is also known as governing equation of conductive heat transfer. We're going to study that. So before we start, I want to tell what are the notations that we are going to use. So Q will be the energy or heat, we can say heat energy. Q dot will be Q by T, that is obvious. And small q dot will be flux, that will be Q dot by A or Q by TA. Now, so before starting, we have to know that this Fourier law, so it is the basic law. It says that Q dot, that is flux, heat flux, depend on temperature gradient. Temperature gradient. So if we replace the proportionality constant, we'll get a constant. We'll get this is known as coefficient of conductive heat transfer. Heat transfer. So this is just nomenclature. So we have to know this. I'm rubbing this. Now the thing is, these equations are in one dimension, that is dt, that is t is changing with x, dt by dx, t is changing with x, but we can convert this equation into three dimensional. How we are going to do that? We are going to take element, so elements will be cuboid here. Now I am going to solve a general equation, so cuboid will be at x with edges delta x, delta y, delta z. So this is x, this is y, and this is z directions. So this will be x, this point will be x plus delta x, and if this point is y, this point will be y plus delta y. If this point is z, this point will be z plus delta z. So we are going to use these notations in this. So let me just rub this because it will look clumsy. Now, before proceeding, I want to tell you that we are going to do a basic thing, that is this should be known. So this will be energy conservation law. So this is what we are going to use in every thermodynamics problem. We are going to use energy conservation equation in every thermodynamics problem. So now energy conservation. So for x we can write heat getting in x direction, that can be written as q dot x, and heat leaving out can be written as q dot x plus delta x. So energy conservation says that heat getting in and heat minus of heat getting out plus if any heat generation will be equals to mc delta t. Okay, now since these are rates, so we should write this as by t. So this can be then written as del temperature by del time. Now this is the basic equation that we are going to use, but for getting the final form, let us first assume that this is 0. We can in last we can just assume that it was not 0 and we can just manipulate the equation, but for the sake of ease we are going to assume that this is 0, so we can remove this. Now q dot x minus q dot x plus delta x, we know this is written as q dot x plus delta x can be written as q dot x plus delta x times of q dot dash plus delta x square by 2 q double dash x and so on. These terms will be nearly 0, so we'll neglect this. So we'll get this as q dot x plus delta x times of this. So substituting this in the equation, we'll get q dot x minus q dot x minus delta x times of q dot dash x. This is basically del q dot by del x, so it's not a big deal to deal with this. Now mc del t by del t. Now let us further solve the equation. So this things will get cancelled out and we'll get delta x del q dot x by del x equals to mass can be written as volume into density. So density and volume can be written as uh, delta x thickness times area, and this area will be delta y into delta z, delta y delta z volume delta x times c del t by del t. So delta x is getting cancelled out. Now what is q dot x? Q dot x is ka del t by del x. So we can substitute that, assuming that k and t are constant. That is very important. Assuming that k and t, sorry, k and a, sorry I said t by mistake, k and a are constant. We can take them out. We'll get minus and minus, there will get plus, plus k a will be left out with del 2t by del x2 rho delta y delta z c del t by del t. Now what will be the area of this flux? It will be this area. So this area is actually delta y by delta z. So this area is actually delta y by delta z. So this can be cancelled out from this side. So we'll get k del 2t by del x2 as rho c del t by del t. Now suppose this thing is done considering y and x, y and z are not contributing anything in x direction. Now if we consider y and x as fluxes from y, uh, q dot z or something q dot y, so we'll get the similar equation, and the equation will be del 2t by del x2 plus del 2t by del y2 plus del 2t by del z2 equals to rho c del t by del t. So I'm going to rub the rest of the things, so please carefully note it down if you want to. Now now we were left with this equation. Sorry, we were left with this equation. So this equation was when we considered that q generation was 0. What if we had a q generation term? So there would have been no problem, because it will be written as q dot gen by volume plus k del 2t by del x2 plus del 2t by del y2 del 2 T by del Z2. So the final equation would be something like this. And this thing can be written as heat generation per unit volume, gen per volume. And this thing can be written as del square T. So the final equation that we get is K del square T plus Q dot gen V is rho C del T by del T. Substituting K that side, we'll get where 1 by alpha is rho C by K. So this was the proof of governing equation for conductive heat transfer. I hope you understood the governing equation, three-dimensional equation. So for any doubt, just write the doubt in the comment. I will try to solve the doubt in the next video. Thank you very much.